For our last example regarding splines, we'll be using the textbook's example for cubic splines and starting with a reference of equation 689. That's the one you'd want to highlight. This is the one we're going to be referencing on the future page to describe and determine A1, A plus 1, A of I plus 1, and A of I plus 2, a whole series of unknown second derivatives that help us determine the spline layout of a set of data given to us here. So obviously example 6.8 on page 234. And you start by determining all of the different gap dimensions, all the different h's. So the gap between 11 and 8 would be a distance of 3. The gap between 15 and 11 is 4. 18 and 15 is 3. 22 and 18 is 4 again. So that's all they've done here is populate the array of h lengths. Then all of these equations, I equals 1, I equals 2, I equals 3, which is curious, first of all, there's only 3 equations, are determined, again, by the setup 689 on the previous page. There are 5 data points. You'd expect there to be 4 equations, right? But there's only 3 required to determine all of our unknown A constants. Remember, spline or cubic splines, natural cubic splines especially, have a 0 second derivative at the left-hand and right-hand side. So both of those sides are assumed to be 0 derivative. It is curvature continuous through the middle, and it all just kind of works out. So in this case, you have h1 be the distance in gap 1. A1 is unknown. Twice times these distances times a2 plus h2 times the second derivative 3. Excuse me, the unknown a coefficient, which more or less indicates or represents our second derivative, subscore 3. Everything on the right-hand side is a known numeric value you can plug in and solve the linear system of equations. But in this circumstance, we only have 3 equations. Each equation only has 3 unknowns. So look how small the matrix for solution of a cubic spline is in comparison to a quadratic spline. If you want to see an interesting comparison, the same data set is done in an example in your textbook. 2 or 3 pages back. Let's flip one more. That is the data set for the quadratic spline fit. So somehow by going to a higher order, you drop how many ranks in matrix size? Those are totally worth it. Just invert that thing, multiply, you're done. You have the values for A2, A3, A4, A1, and A5 are 0. And then you just go straight into invert, multiply, find the solutions, and write your 4 equations down. The highlighted equations are the spline fits for each one of the gaps between points, and those splines are depicted here in the bottom right-hand plot. In this particular case, they asked us to find a y value for the x location 12.7. Well, you'd have to look to see which spline is used in the gap that contains 12.7, and it looks like from these ranges, 12.7 lies between 11 and 15. So we would use this equation to find the y value that this spline function correlates with 12.7, and that ends up being 10.11, which is a little bit different than if you look back a few pages again at the quadratic spline. They used the same exact data, same exact location, and found 10.4898 there in the bottom hand left side, right by the pinky. So a very useful tactic, especially because of the 0 derivatives on both the left and right hand side. They're very easy to populate equations for fitting. Natural cubic splines are very, very nice to use, because you get a little bit improved result, curvature continuity on every interior point, without really much added complexity whatsoever.